Now that we've done our example of CSTRs in series and seen how that gets us closer to the kind of phenomenon we see in a plug flow reactor, we can come back and spend a little bit more time on plug flow reactors. In this video, I'm not actually going to solve more problems related to plug flow reactors, but instead, I want to remind us of the design equations and kind of bring up the concepts and substitutions like we had before for conversion, bring up the topic of residence time. I want to expand on the subject of reactor sizing and the possibility of reactors in series by going over what are called Levenspiel plots. And these are really nice visualizations for analysis of chemical reactors. And then I'm providing a roadmap here this time rather than me just kind of rambling at the beginning of the lecture. But I just wanted to give you a sense that what's coming next is we'll go back to batch after this. You'll see some PFR problems, you know, as homework, and you'll get enough practice with them. But what we wanted to next introduce is this concept of variable mass density. And we're going to start with a simple system that has no flow. So we're going to end up with this unusual case of variable volume batch. But that's the next video. So let's go ahead and focus on PFRs here. I'm going to go back and remind us from our generalized balance. We were able to derive from first principles equation 3-26. And that was for PFR. So we have dVr. Oh, and there's actually nothing on the denominator here. At least as written this way. It's dVr equals d molar flow rate of I over Ri. This is our PFR design equation. Okay. So now what I want to do is introduce fractional conversion. So in terms of fractional conversion, what we can remember here, and I'll show the steps here since this equation involves differential terms. We know that if we want to define conversion, molar flow rate of A, if I just pick species A, equals FA naught times 1 minus conversion of A. So now if we want to imagine the derivative of taking sort of the differential of each side, on the right-hand side here, this is a constant, so that term doesn't matter. And here we have our derivative with respect to conversion, which is going to have this coefficient of FA naught, and it's going to have a d conversion of A. So imagine that this is what's happening in a differential slice of your PFR. This is the change in molar flow rate along that slice, within that slice, and this is how that depends on conversion. Okay, so if we want to make this substitution, just to stay on the same page, I'll go ahead and work over here. So if we want to substitute this back into here, that should give us dVr equals, and now we can just put this on the numerator here, negative FA naught times dXA over Ri. But since we've used A, and we'll call this let's see here. We'll just write RA. Great, okay. And we can rearrange this a little bit further. Sorry to work from right to left. But again, just to have this on one page, we can write dVr over FA naught. That's dVr over FA naught equals D. Okay. Getting the keyboard by accident. Okay, equals d conversion of A over minus RA. So what did I do here? I moved FA naught to the denominator of the left-hand side, and then I just brought the sign down. And I will go ahead now and use a different color just to highlight that this is the PFR design equation in terms of conversion. And that, oh man, lots of color challenges today. Okay, that is equation 3-27 in the Roberts textbook. So that's how you can get the PFR design equation to look in terms of conversion. So you can do a little bit more here. Let me go to the next page for that. So you can convert equation 3-7 to include residence time. And if you were to do that, you get this. D tau naught equals CA naught times dxa over minus RA. This is equation 3-29 in your book. And a couple of things here. For PFR, again, tau naught, the residence time has the same definition of your volume of your reactor over your initial volumetric flow rate in. We can also say that if you have constant density or gases with balanced stoichiometry, this is just our whole incompressible fluids bit, although it's important for maybe us to point out that gases with balanced stoichiometry can be treated just like they were incompressible. Then you just have 1 tau the whole time, and that's just this expression here. Okay, so you know, we've been going through the process of working with residence time and conversion. So hopefully you can recognize why that's all useful. I want to do a couple more transformations and rearrangements just to get you the most useful PFR design equation, which we haven't covered yet. So we're gonna work with this, but we'll keep going. Let's see what happens when we substitute the definition of conversion back in. Okay, so if we want to put things back in terms of concentration rather than conversion, maybe for a PFR, then here's what happens. So substitute the definition of XA, and that gives us d tau equals minus dCA over minus RA. Now, if you're wondering where did the dCA come from, well, I'm just relating conversion back to CA, and that's also how the CA naught cancels out, and where the minus sign comes from. So if you're a little uncertain about that step, just you know, think about how this minus dCA can come from CA naught and dXA. And there's a faster way to get here too. If we go back for a moment, so pay attention to this form. We got this minus dCA. If we go back to the previous page, we already showed you here how you could go from a change in the molar flow rate to this conversion, this differential conversion times a starting concentration. So all we've kind of done is actually jump back and forth a little bit. We had dVr, dFi over Ri, which maybe looked simple, maybe not. If we wanted to work in terms of conversion, we got to here by making the substitution. If we want to work in terms of concentration and residence time, then what we're doing on this page is getting back resonance time in. And because resonance time includes this volume over volumetric flow rate, now we actually we would rather go back to concentration rather than molar flow rate. So this can tell us what the concentration is at any given time within the reactor. And in fact, if we rearrange this and cancel out signs, well, first let me just say this is equation 3-31 in the Roberts textbook. So, you can see all of these steps and equations in between, though I don't think they're as important. And so if we just work with this form a little bit further, let me go to the next page to do that. We can, let me just rewrite. So d tau minus dCA over minus RA. So if we cancel out our minus signs, we have this. But now if we kind of swap these terms a little bit here, we have RA equals dCA over d tau. And now my question for you is, does that look familiar? So I want to pause for a moment and sort of just ask you, have you seen this form of an equation before in another system? And hopefully you're thinking, yeah, that actually reminds me of batch, because if you recall a batch reactor at constant volume, batch reactor, constant volume, we had Ri equals dCi over dt. And so now the only difference is instead of t, we have tau. So I wanted to make a little bit of a point here. Part of the reason why we like resonance time, I think it's better illustrated in this example than in the CSTR example when I first brought it up, is because at least in the case of a PFR, it allows us to put the expression, the design equation, into an almost identical format as batch reactors. And so you've got this differential equation. In terms of the math from here on out, you already know how to solve these kinds of problems. You know precisely how to work with dCi over dt. So now you're just doing it in the context of a PFR, but you have this d tau, and that's really the only difference here. So I don't think we have to spend as much time showing you how you might work through a PFR when you have this kind of design equation. And hopefully over the course of all these videos so far, you've now gotten a better sense of both why you might want one version of the design equation versus another, and why we're also doing, I guess it's basically the same point, but why we're going from one to another. So that's our PFR design equation.